Few faults can destroy track geometry as quickly as voiding. It's the hidden gap beneath the rail and sleeper that turns every passing wheel into a hammer blow. You might think the biggest risk to trains are broken rails or track buckles, but it might just be a void. It starts small, but left untreated, it ends in derailment. In this video, I'll show you what voiding is, why it matters, how it develops, and how engineers deal with it. By the end, you'll see why voiding is one of the fastest ways to destroy track geometry. And I'll also give you a preview of one of its biggest drivers, water. So voiding is dangerous and can lead to a train leaving the track. But what actually is it? In good, well-maintained track, the sleeper is fully supported by the ballast. But this isn't always the case. In some places, there will be a void. A void is an empty space. In the case of track, it's an area where there is no ballast under the sleeper. No ballast means no support. Not so much of a problem if it occurs at the centre of the sleeper, but if it's to the side, under the rail, and large enough, that's where the problems start. As trains pass over, the huge weight transfers from the wheel to the rail and then to the sleeper. From there, it should spread down into the ballast. But if there's no ballast beneath the sleeper, the only thing that happens, pushing until it contacts the ballast. When the weight of the train passes, the sleeper rebounds back up, just in time for the next wheel to pass over and repeat the process. It's important to remember that voiding is different from normal settlement of the track. Voiding is a localized loss of support under one or more sleepers. Settlement, by contrast, is uniform sinking of the whole track. Settlement should be expected after the renewal of ballast or the full renewal of the track as the ballast compacts and consolidates. However, if it happens in older track, it could signify underlying issues. Now, before we look at how engineers tackle voiding, a quick word about the sponsor of today's video, Worsens. It's always better to be on the front foot with maintenance, proactive rather than waiting for inspections or reported rough rides. Worsens' VoidSense technology detects voiding and undertrain movement in real time. The sensors continuously monitor support beneath the rails and sleepers, with data sent back through the RailSense hub, giving maintenance teams early warnings of problems before they become derailment risks. RailSense also provide other monitoring solutions, from buckle sense for hot weather buckles to track water for drainage. But when it comes to voiding, VoidSense puts engineers ahead of the problem. You can find out more at railsense.co.uk, and my thanks to RailSense for supporting this video. Voiding is dangerous for a number of reasons that are interlinked. The most obvious is the repeated stress on the components in the track. The movement caused by the void stresses the rail and fastenings as they move repeatedly under each passing wheel set. If the voiding is very severe or sudden, there can also be a shock or impact element to this stress as well, further increasing that stress level. This leads to an acceleration of wear on the track. If joints are present, battered rail ends can occur, and the repeated impact loading can also accelerate surface defects, such as squats. Sleepers, particularly the more rigid concrete ones, can crack, fastenings can work loose or become deformed, and the continued impact on the ballast can cause it to break down. As well as the impact on components, there is also the track geometry to consider. Voiding can become a top fault, a twist fault, or cyclic top, depending on the conditions and the other factors. And because voiding so often shows up as a geometry fault, like those top, twist, or cyclic top faults, this is a good moment to point you to my free track geometry email course. It's designed to help you understand how track geometry shifts over time and what engineers do to keep it safe. The link's in the description and the top right hand corner now. All these geometry faults I've spoken about require rectification within strict timescales, which tells you how severe the danger is they pose to trains. And that's just when voiding is in plain line. When you have voiding in switches and crossings, the stakes are raised further, with higher forces moving rail sections and wheels transferring from one rail to another. S&C carries a higher level of inherent risk, even without voiding. Voiding under crossings can lead to high levels of damage to the crossing nose. Crossings are large, expensive items that are time-consuming and potentially tricky to replace, so damage to them is really not ideal. Then there are switches, with their free-ended switchblades. Switchblades rely on slide chairs underneath them for support while allowing them to move as they need to. Voiding removes that support, allowing movement in one of the key places track engineers don't want it. So voiding is dangerous and causes real issues for components, and it's something you really don't want in S&C. But how does it form and get to the point where it's a danger to trains. Let's start with how a void forms in the first place. Ultimately, if we're looking at the start of the void, we need to ask, what can cause ballast to stop supporting a sleeper? First, the ballast itself. If the ballast wasn't sufficiently compacted during installation or through tamping, it can continue to settle under traffic. Some settlement is to be expected, and the use of temporary speed restrictions and follow-up tamps helps mitigate this risk, but large or uncontrolled settlement is where problems start. If that settlement isn't uniform, gaps can open up between the ballast and the sleeper, and a void is created. Then there could be the quality of the ballast. If the stone isn't strong enough to withstand the forces, it will begin to break down under loading, reducing support to the sleeper. We also need to look above the sleeper, at the rail. Joints are weak points, and they allow movement of the rail ends and concentrating forces into the ballast below. Voiding at rail joints is a frequent fault, which can lead to the joint failing. Looking back below the sleeper, formation and drainage issues play their part. The ground beneath the track isn't always uniform. Localized soft spots can offer less support, leading to voiding. And then there's one of the main enemies of track. Water is one of the biggest drivers of voiding. When drainage is poor, water becomes trapped within the track structure and starts to affect both the formation and the ballast. A saturated formation loses strength and deforms under load, while fine material is pumped up into the ballast. Those fines foul the ballast, and in the presence of water, reduce interlock between the stones. The ballast may still be present, but it no longer behaves as a stiff, load-spreading layer. Support becomes uneven, and that uneven loss of support is what allows voids to form beneath sleepers. This condition is commonly known as a wet bed, and I've covered it in more detail in another video of mine linked in the top right hand corner. And because drainage sits at the heart of this, I've also got a dedicated drainage video linked in the description and the top right hand corner now as well. Possibly the worst part of voiding from an engineer's perspective is that it becomes a self-reinforcing loop. Once a small void is formed, the movement leads to impact on the ballast, which breaks it down further. That increases the void, which creates larger movement, which creates larger impacts, which degrades the ballast even quicker. The fines created as the ballast breaks down also blocks drainage, compounding the issue even further. So the cycle continues. Bigger void leads to greater impacts, speeding up deterioration and creating even bigger voids. It all sounds pretty doom and gloom, but voiding can be addressed. There are a number of options available to sort voiding, and they range depending on how bad the issue is. The simplest and easiest to undertake fix is manual lifting, packing, and tamping. This involves, as the name suggests, lifting the track, filling the void with ballast by hand with shovels, and then using manual vertical tampers. The vertical tampers vibrate the ballast, helping it move into the void, but also consolidating it. This method can be used as a short-term immediate fix for bad sites to protect the safety of trains, while a longer-term fix is planned, but it can also be effective on sites where voiding is minimal as an early intervention. The next step up would be to bring in the tampers or stone blowers. These specialist trains address the issue two distinct ways. Tampers, similar to the manual handheld vertical tampers, vibrate the ballast. However, they also pick up the rail, allowing more ballast to be packed in by the tines that squeeze the ballast into the area under the sleeper. Stone blowers, as their name suggests, blow small graded stone chippings into the area under the sleeper. This fills any void and restores support to the sleeper without disturbing or damaging the existing ballast as much as tamping. If these fixes don't solve the problem, the next step is to clean or replace the ballast, restoring its ability to drain and support the sleeper. For smaller sites, this would entail digging out the old ballast and backfilling with new. Tamping, either manually or with a machine, is then used to ensure it's consolidated and fully supporting the sleepers. For longer sites, ballast cleaning machines can be used, but these face significant logistical and cost limitations. If the ballast is removed, there's also the opportunity to address further formation issues. Typically, this would involve a geotextile, a specially engineered material placed between the formation and the ballast. It provides separation while still allowing water to drain through. At the most drastic end of the spectrum, in terms of interventions, is a full track renewal. This allows underlying issues to be fully addressed, all components renewed to full strength, and any required formation treatment to be implemented. When it comes to sites with reoccurring voiding, the focus must always be on tackling the underlying cause, not just filling the gap. Voiding is the local loss of support under sleepers. Each passing wheel turns it into a hammer blow, accelerating wear, creating geometry faults, and, if left unchecked, raising the risk of derailment. development. It starts small, but the feedback loop of movement, ballast breakdown, and water makes it worsen fast. Engineers have a range of interventions, from manual packing to full renewal, but the key is identifying and treating it early, before damage escalates. That's why voiding is one of the fastest ways to lose track geometry, and one of the clearest signs of deeper track problems that need fixing. If you found this video useful and want to go deeper into track geometry, make sure to sign up to my free track geometry email course. The link's in the description, and don't forget to subscribe so you don't miss the next video.